Hello dear students. So in the last lecture we have seen how we can write the displacement in spherical polar coordinates and how we can transform the coordinates x, y, z to lambda, theta and phi. So here we are used to these three coordinates, right? Then in a spherical symmetry, if we are talking about motion on the surface of the earth, then the analogous coordinates are the longitude, the latitude and the altitude. So we have seen how we can write dx in terms of d lambda or the other way, and how we can write dy in terms of d phi, and how dz is equivalent to dz, right. So we have seen this, right. So in today's class what we will do is we will try to write the total differentiation of a vector in a rotating frame of reference. So the topic is the total derivative or total differentiation. Total differentiation of a vector in rotating frame of reference. So a rotating frame of reference or a non-inertial frame of reference. So for example, so what is the reason? I mean, why do we want to see how the total derivative of a vector will look like in a rotating frame of reference? So the Newton's second law can be used to derive equations that describe the conservation of momentum, right. So even when we wrote the first governing equation, it is derived out of the conservation of momentum. So which is indeed one of the basic principles of atmospheric dynamics, right. So this law applies to motion in inertial frame of reference generally, right. So where we say that if you are able to write the rate of change of velocity per unit mass as a sum of forces, it is generally by default applicable to things which are moving in an inertial frame of reference. But when you talk about a non-inertial frame of reference, then what do? You add some apparent forces on the right hand side. Then you say that the motion or these apparent forces are just because of the acceleration of the frame of reference or the movement of frame of reference, because you assumed that frame of reference is fixed, and then with respect to this frame of reference you are trying to describe the motion. But when you realize that this frame of reference itself is accelerating, then you need to add some more additional terms. So in order to apply this law in a non-inertial frame of reference, we either need to consider apparent forces that arise due to the motion of non-inertial reference frame, or we need to relate acceleration vector in the inertial frame to the non-inertial frame. So the one way of doing it is either add apparent forces, or you write the acceleration vector, let us say from you write dv by dt or dv by dt. So you write how you can write this equivalence. That means you relate acceleration in the non-inertial frame of reference to the acceleration in the inertial frame of reference, right. So let us consider, now the topic is we have to see how the total derivative of a vector will look like in a rotating frame of reference. Now most importantly, we should ask ourselves, what is a total derivative? Total derivative accounts for change in a physical quantity while following the motion. That is the most important thing. It accounts for the change with respect to time per se, but while following the motion. So it is different from an ordinary derivative, or let us say a partial derivative, in that particular way. So now what we are going to do is, we have already seen how we can add the apparent forces. Now let us see how we can write the acceleration vector between an inertial frame of reference and a non-inertial frame of reference. So for this purpose we will consider a vector A. Let us say A is a vector. So how do we write A? We write A as Ax bar I cap. So I am writing all the components in terms of primed coordinates. So, Ax prime I cap prime plus Ay prime j prime plus Az prime k prime. So, what is this? This is the vector or this is the vector in an inertial frame of reference. So, we take the inertial frame of reference, then we assume that the vector will look something like this. How do we identify the vector? In the inertial frame of reference, we identify it with primed coordinates. The magnitudes are of A, which are Ax, Ay, Az along the three directions are indicated with the help of a prime. Okay, and so are the unit vectors. Right, and the same vector, if you are viewing it in a non-inertial frame of reference or in a rotating frame of reference, right? How do we write it? We write them without the primes. So, Ax I cap plus Ay j cap plus Az k cap. So, this is the same vector. Yeah, this is the vector A, which is in a rotating frame of reference. How fast is it rotating? It is rotating with an angular velocity omega. Now, we need to find out a relation between these two. Right. Now, let us say we are talking about the total derivative. We are trying to derive the total derivative of a vector. Right. So, let us say we write dA with a suffix a, dAA by dt is the total derivative in the inertial frame of reference. This one is the total derivative in the inertial frame of reference. So, the suffix a is indicating the inertial frame of reference. So, how do we expand it? dA a over dt will look like, since we are talking about the inertial frame of reference, dAx by dt along I cap, the primed unit vector day by dt along j cap plus d Az by dt along k cap. Right. Now, see, this is with respect to the inertial frame of reference. That is why I did not actually bother to take the derivative of the unit vector. Okay. Now, this can also be written in terms of the components of A, the components of the vector A in the non-inertial frame of reference, because vector A, which we are trying to transform, is identified both in the inertial frame of reference as well as in the non-inertial frame of reference. This is what it looks like, the variation in the inertial frame of reference. We can change it in terms of non-inertial frame of reference. So, let us say how we write it. So, this is dA A by dt is equals to dAx by dt plus Ax di by dt plus Ay by dt plus right. So, what have I done? I have replaced using the magnitudes along the rotating frame of reference. Let us say if they are rotating, the only difference, where does it come? The difference comes in accounting d by dt of I cap, d by dt of j cap, d by dt of k cap. And since this derivative is taken with respect to the inertial frame of reference, I still have the suffix a intact in this picture. So now let's say, what do these terms represent actually? What are these terms? These terms. So most importantly, what is this term? What is this term and what is this term? Ax magnitude component of A across x multiplied by the inertial derivative of the unit vector along x direction. Ay, which is the magnitude of A, the component of A along y multiplied by the inertial derivative of j, and similarly along the k. So, what do these terms represent? So, why these terms are existing to begin with? If these terms are not there, what will be the inference? So, these terms are existing just because the moment the reference frame starts to rotate, the I cap, j cap and k cap, which are pointing in a particular direction, they also rotate along with the frame of reference. So, if there is a rotation, then obviously the direction is what is being changed. So, it is necessary for you to accommodate or account what is the acceleration that is coming into the picture just because of the rotation of the unit vectors. Right. So, if you write the total derivative, let us say if you write the total derivative with respect to the non-inertial frame of reference, it looks like dAx by dt I cap plus dAy by dt j cap plus dAz by dt k cap. So, this is the total derivative in the non-inertial frame of reference. Right. Now, let us see in the rotating frame of reference. So, now we have to see how do we write d by dt of I or d by dt of j or d by dt of k. So, this is very important. How do we find out d by dt of the unit vectors? So, for example, let us say if this is a coordinate system, if your unit vector I cap is in this direction, j cap is in this direction, k cap let us say is in this direction. So, the coordinate along this is lambda, the coordinate along j is called as phi, and the coordinate along k is z, right. Now, the rate of change of unit vector I, let us say delta I. What is the delta I? Delta I is the change in the I unit vector, can be written as let us say dou. What are the dependent variables here? Dou I by dou lambda into delta lambda plus dou I by dou phi into delta phi plus dou I by dou z into delta z. Right. So, what is this? This expression is relating delta I, that is change in I, to longitude, latitude and the height, right. Now, if you consider, before I move ahead, so delta I is telling you what is the change in I with respect to latitude, longitude and the altitude. Now, if you take a solid body rotation, if you do not bring in the very small deviation from a perfect spherical geometry of the earth and you consider it as a solid body, and if you assume it to be rotating from west to east, for a solid body rotation, if the rotation is happening only in this direction, let us say, we can write delta lambda by delta t. The rate, let us say you consider one particular point, the rate at which if this point, changes across the latitudes, across the longitudes per unit time, what is it? What can it be? It can be equal to the angular velocity. You consider a perfect sphere, you put a point, the rate at which this point sees different longitudes with respect to time is nothing but the rate at which the object is revolving around itself. And what is the rate at which the object revolves around itself is called as, it is called as the angular velocity, which is omega. And if there is no variation, or if the body is not rotating across any other direction, you would simply say that delta phi, there is no change in the latitude, there is only change in the longitude. And if there is no change in the altitude, you say that delta z is equals to 0. So, if you use this conditions into delta I, you will realize that delta I, the incremental change in the unit vector I is nothing but, so dou it becomes dou I bar by dou lambda into delta lambda, right. Now, if I divide this expression by delta t, right, what will I get? I will get dou I by dou lambda into delta lambda by delta t, right. And if I make the limit delta t tending to 0, I can write this as dA I by dt is nothing but dou I by dou lambda into dou lambda by dou t, which is nothing but dA I by dt is equals to omega dou I by dou lambda, right. So, what is omega? Where did I get omega from? Dou lambda by dou t is nothing but omega. What is omega? Omega is the angular velocity of the earth, right. Now, what have we got? We have realized one simple expression. This expression is giving you that the rate at which the total derivative of the unit vector is equals to omega times dou I by dou lambda. Now, the body is rotating. Now, the total derivative seems to be dependent on the angular velocity, and then the rate at which this unit vector is changing with respect to lambda, with respect to a given lambda. You take one given lambda and see how you can see the change in I, or you can say that when you are changing lambda from this point to this point, what is the change that is going on in I? Why I should change to begin with? Because there is rotation in the frame of reference. Now, if you look at this, let us say we consider this, how does it look like? Let us say we are looking from the top, let us say we are looking from the northern hemisphere or the north pole to the down. So, you see let us say this point is what? This point can be assumed to be at a longitude lambda, and this point can be assumed to be at a longitude of lambda plus delta lambda. Right. Now, what are we trying to do? We are trying to visualize how does the change in I come about with respect to lambda. So, here the initial point that you have is lambda, and this point after some amount of time. So, here you are looking from the top and you are seeing that an object is moving from west to east like this in a counterclockwise direction, because that is what it appears to be for an observer from the north pole, right. So, this change on the other hand, if you look in the regular coordinate system, this change appears to be equal to delta x, right. Now, where is the unit vector now? Unit vector, this is the unit vector I, right. This is the unit vector, and after a moment of time when the object or when it reaches here, this is nothing but this is I plus delta I, right. Now, this is what? This is delta x, and this becomes delta lambda, because delta lambda is the change in the longitude, right. Now, if this is delta lambda, this is obviously delta lambda, right. Now, from the simple vector addition, you can realize that this resultant is delta I, right. So, delta I is the vector which points towards it appears to be pointing towards the axis of rotation, right. Now, from this figure, what we can see is that we can clearly see that the direction of dA I by dt is towards the center of rotation as when delta lambda simply tends to 0, right. So, what can we write? We can write that, can simply write that dA I by dt, what is this, is directed towards the center of rotation. Towards the center of rotation. So, this is one important reference, one important inference that you can see from by looking at how lambda and the unit vector I are related to each other. Right. Now, if you say that dA I by dt has a magnitude equal to omega, then we can write, we need to look at the same time how does the unit vector j, change in j will look like. So, let us say we consider something like this. Now, the j unit vector is of course directed in the direction of latitude, right. Now, let us say if you consider this to be a point at a latitude of phi, right. Now, this delta I that we have seen from this figure is actually in the direction towards the axis of rotation. In this figure, it may not appear as if it is towards the axis of rotation, rather it appears that it is directed towards the center of the earth, right. But if I can draw it even, one more time, it will be very easy to realize that delta I, what is delta I? Delta I is the change that is brought in because of the rotation of the frame of reference. So, now we can see one thing, one very important inference is that it is directed, the change delta I is directed towards the axis of rotation. What is the difference? So, if you consider the earth to be like this is the axis of rotation and this is the center. Now, the delta I is directed in this way, not in this way, no, this is the direction. Now let us say, so if delta I is in this direction, how can we write delta I in terms of other unit vectors or other variables that are available, right. So, here it is what I have drawn. So, now we have realized that delta I is of course pointing in this direction, right. Now, if you consider, let us say this vector away is basically k cap, or this displacement is nothing but delta z. So, if this is k, then you can simply write at any given point, if this is k at any, and this is phi, and this is let us say k cos phi. So, you can write this the other side as minus k cos phi. So, this is minus k cos phi, the magnitude, and the vector that is along the surface is this, right. So, this is the vector that is this one. This one is nothing but j sin phi, right. By using these two, j sin phi and minus k cos phi, I can write delta I in terms of these two quantities, right. So, then I can write dA I by dt is equals to, if omega is there, right, omega times j sin phi minus k cos phi. You are able to see here, it is j sin phi minus k cos phi. So, dA, or we can write dA I bar by dt is omega j sin phi minus omega k cos phi. So, this is a very important expression. So, let us say we will use it later, right. Now, so how do we write omega as a vector? Because this appears as if omega is multiplying these two quantities. Now, if I want to resolve this, I can write omega, the angular velocity, in its vectorial form as 0 I bar plus omega j cos phi plus omega k sine phi. If I use this, then I can write dA I by dt is nothing but omega cross I. The total derivative of the unit vector I, the inertial derivative is nothing but the cross product of angular velocity and the vector itself. So, now if we go back, if we substitute everything, so we can get the similar kind of expression for k and j, then we can write the dA, the inertial derivative of a with respect to time as dAx by dt I plus Ax dA I by dt plus dy by dt plus right. So, if I put everything, then I can simply write, yeah, this is what the total derivative of the vector, the inertial derivative of the vector is nothing but it is dA over dt, because if we go back here, yeah, so dA by dt, this is what it is. So, I am using it directly. So, it is dA by dt plus omega cross A. Right. So, omega cross A. So, the total derivative of a vector in a non-inertial frame of reference is related to the total derivative of the same vector in the inertial frame of reference like this. So, what is it? We only have an additional term, additional curl term. What is this curl? Curl of the vector with the angular velocity, right. So, this discussion is something about how we can transform the rate of change of a vector from an inertial frame of reference to a non-inertial frame of reference.